A matrix is a rectangular array of numbers arranged in rows and columns, placed inside brackets. Matrices, so we got matrix and matrices. Matrices is the plural form of a matrix. Elements are the numbers inside the brackets of a matrix. Okay, so let's start off with a couple of examples here. So 4, 3, 1, 2, 5, 0, negative 7, 8, 3, 4, 6, and negative 5. Okay, so that's one example of a matrix. Another matrix, just do a single row, 1, 5, negative 2. That's a matrix. We'll do another one. So 1, 2, 4, 6. That's a matrix. And when we talk about elements, so these elements right here, these refer to individual numbers inside the matrix itself. So we're not separating anything with commas. We're just using the location to indicate the type of variable. So what I want you to think about is in our last lesson, right at the end, we solved a system of equations that had 3 variables in it. There's a lot of things to keep track of. Okay, well, what if I told you that there's a way to solve a system without having to write the letter? In other words, I know what x and y are, so is there a way that I can use position to keep track of the variable rather than physically having to rewrite the letters x and y? I know it doesn't sound like it's going to save that much time, but if we look at some rules about organization, it's going to save us a little bit of effort and, yes, some time than doing it by hand like we did the other day with just having to write it out by grouping equations together and eliminate a singular variable. Okay, so today we're going to look at something called a matrix. So we're going to solve matrices using, we're going to use matrices to solve a linear system of equations. Whereas in the past we've used just a substitution and elimination. And those methods are great when we're dealing with 2 variable systems, but what if we have more? Right? And that's sort of the intention, is that the more complicated the problem, the more the amount of time and the more the amount of effort it's going to take to get there. All right, just to kind of remind us of the 2 variable versus the 3 variable system. So in 2 variables, I might give you something like 3x minus 4y equals negative 2, and x plus 2y equals negative 4. And we would use substitution or elimination to solve that. And we would get our solution would be, now I'm just going to tell you the answer in this one since it's not the intention today. So the solution to that system is negative 2 comma negative 1, or it looks just like an ordered pair. Okay. Now in a 3 variable system, so I'll give you x plus 2y minus 5z equals negative 9, 4x minus 7y plus z equals 30, negative 3x plus 4y minus 6z equals negative 24. Okay, and as far as solving that one goes, it's possible to use the earlier methods to solve it, but it's very time-consuming, a little bit challenging to keep track of everything. So in this case, we're going to emphasize that matrices would probably be the better one to use to solve that. And our solution again, so I'm just going to tell that to you, for something like this would look like 2 comma negative 3 comma 1, and it would be some sort of ordered triple. versus an ordered pair. Okay. An augmented matrix is a matrix with a vertical bar separating the columns into two groups. We usually have an augmented matrix to rewrite a system of equations. So first thing I want to show you here is how do we translate a system of equations into what's called an augmented matrix. And then we'll go in and we'll look at the matrix rules about how one simplifies a matrix and gets that to actually give us some sort of answer. So for a system of equations, what I want to do is I want to set up a bracket, and I'm not usually going to write this, but the first number is going to represent x, the second number is going to represent y, the third number is going to represent z. Then we're going to draw in that vertical bar, and this is how we communicate that it's an augmented matrix. And then we're going to put our constant, sort of the number that's on the other side of the equal sign there. Okay, so in this first example, just look at our numbers here. So we have 3x plus y minus z. So 3, 1, and negative 1, with the constant being 9. Then we have negative x minus y plus 3z. So negative 1, 3, and 3. And then the last row would be 1, 2, negative 1, and 0. Now, how do you do it when you're missing some information? So we still have the first three columns are the variables, x, y, and z, but we just have to put zeros in any place where something's missing. So let me put my augmented line here. Sort of close that out there. Okay, so we have the first the first row would be 1, negative 3, 2, and negative 12. The second row, we don't have any x's, so 0 x's, 1 y, 4z, negative 3. And then the last row would be 0 x's, 0 y's. We have actually 1 z, sorry, I miswrote that, 1 z, and that happens to equal 2. And then the last one, so let me set that up, put my augmented line. Okay, so we have 3 x's, there are 0 y's, and negative 5 z's, and then negative 12. Then we have 0 x's, 4 y's, negative 1 z's, and a 5. And then 2, negative 3, there's a 0 for the z's, sorry, and negative 4. Okay, so that's how we translate a system into what's called an augmented matrix. Okay, echelon form, it's actually pronounced echelon with a sh sound instead of a cha. Echelon form, a matrix is said to be in row echelon form if there are ones down the main diagonal, upper left, lower right, and zeros below. Okay, so let me kind of point out how these are examples of echelon form here. So if I have ones on the diagonal, so in both cases, ones on the diagonal, and zeros below it, so come in here, see how I got zeros below it, right? All right, so in both cases, they're in row echelon form. Okay, now, what do we do with this? Why is this important to us? Okay, take a look at that bottom row. That bottom row, it says 0, 0, 1, 2. Think about what that means in terms of x's, y's, and z's. Okay, the fact that there's a 1 there, that actually translates into the equation z equals 2. So as far as our solution goes I have one of my numbers. Okay. So if I can get it in that form, I can actually use the idea of back substitution, which we reviewed in the last lesson, to figure out what x and y are. So if I jump up to the second row has a 0, 1, 2, and 3. So that says that y plus 2z equals 3. Well, I already know what z is, so I can just substitute that in. So y plus 2 times 2 equals 3. So that's y plus 4 equals 3. So what is y? And bring the 4 over, we should get negative 1. So at that point I know what y equals. And then we can look at that last equation. The top row, which is the last equation we're going to solve for, has a 1, 2, negative 1, and 0. So that says x plus 2y minus z equals 0. Okay, well I know y and z, so 2 times negative 1 minus, sorry, I meant that to be in black, minus 2 equals 0. So that'd be x minus 2 equals 0. So x minus 4 equals 0. So what is x? X is 4, yay. Okay, so the point being, if I can get my matrix to look like row echelon form, I can then translate it back into a system of equations and very quickly figure out what the solution to that particular system is. Okay. Okay, so if the matrix ever gets into this form, then we would use back substitution to solve. All right, so before we get in here and actually look at some new types of math rules to consider, let me kind of point out our goal and just what it looks like at each stage of the game. So we're going to be given a system of equations to solve. Our first step is going to be to rewrite the equation into its augmented matrix form. Then we're going to do something using row operations, which we'll learn about in a moment, and how to take that augmented matrix to look like the echelon form matrix. Once we get it into echelon form, then we'll use back substitution and actually figure out what the solution of that particular system is. Okay, so if you're ever confused, just go back to this list. This is that's sort of our goal for each stage as to what it should look like.